Okay, so consider an ellipse, shown black here with its two foci, and a point M on its boundary. So I can move M around anywhere on the boundary of the ellipse. Now let's take a second point P, which I can also place anywhere on the boundary of the ellipse. For example, here. Let's connect these 2 points, P to M. And now I'm going to consider the line passing through P, which is perpendicular to P minus M. There it is. So as I move P around, this line also moves around. Notice that it is always perpendicular to P minus M. Now, the overall points on the boundary, if I vary P along the boundary, this family of lines sweeps out an envelope. And we've covered this in another video. I'm going to give you a link in the description. But this envelope is a 3-cusp envelope. You can see here that instantaneously lines through P are always tangent to this envelope, i.e. this envelope is a caustic to this family of lines. Very well. Now, if I move M around, and M is always the anchor point, the shape of this deltoidal, 3-cusp deltoidal envelope changes, but amazingly, its area is constant. So, meaning that as I animate the position of M over all P's, you get this 3-cusp deltoid, and as you can see up here, its area of the deltoid is constant. For this particular aspect ratio we picked, I believe the aspect ratio is equal to the golden ratio. You get this pleasing phenomenon, whereby the area of the ellipse divided by the area of the deltoid is 2. Okay. Alright, so here I want to focus on phenomena associated with the preimages of these 3 cusps. Now, what are these preimages? These preimages, so if I color the 3 cusps as red, green, and blue, each one of these cusps is associated with a point P on the boundary. So let's go ahead and draw P again, and the perpendicular line, such that the instantaneous envelope, for example, right here, when P is on one of these preimages, for example, this blue one, it means that the envelope is instantaneously, or the line going through P perpendicular to P minus M is instantaneously tangent to the deltoidal envelope, but at the cusp. So the preimage of this blue cusp is this blue point, the preimage of this red cusp is this red point, and of this green cusp is this green point. Let's animate P, and we can see how this works out. So for example, right here when P passes through the preimage of the green cusp, right here, it means that the family of lines is instantaneously tangent to the deltoid at the cusp. This is a degenerate situation, but it is well defined. So you can see likewise that when P passes through the red preimage, the line is instantaneously tangent to the envelope at the cusp. So we can define this way 3 preimages associated with the 3 cusps. Very well. Now what we're going to do now is we're going to investigate a different area here, whereas I can draw osculating circles that pass, so circles that are tangent to the ellipse, but tangent at the 3 preimages. Let's draw them. Here they are. So I have a first blue circle, which is tangent to the ellipse, at the preimage of the blue cusp. Likewise, I have a green circle and a red circle. Now, 2 phenomena are spotted right away here. First of all, let's go ahead and erase P and the construction line. The first phenomena that you notice is that the 3 cusps touch each one of the osculating circles, or their circumferences, at a single point. And this happens dynamically for any position of M. The other really interesting phenomenon here is that these 3 osculating circles concur or meet at M. Let's animate M and you're going to see the phenomenon. So as I animate my anchor point M and I keep drawing the constant area deltoids, you can see that the three osculating circles at the preimages of the cusps meet at M. Not only that, the cusps of the deltoids lie on each of the circumferences. Okay, now there's another coordinated phenomenon here. Let me draw the lines that connect each one of the deltoid cusps to the centers of the osculating circles. Magically, these three lines concur at M, and they are diameters, since they connect a point on the circle, which cusps, to their centers. They must be diameters. And these three diameters, shown dash green, dash blue, and dash red here, concur at M. So not only do the circles meet there, but the diameters concur there. Or the diameters defined by their centers and the three cusps to the deltoid. Okay, so here's another phenomenon. I'm going to go ahead and connect the three centers of the osculating circles. So I'm going to turn off these concurring lines, these concurring diameters. I'm just going to connect these three dots. Let's call this the osculating triangle. It turns out the area of this osculating triangle shown up here is also invariant. And if I draw the triangle defined by the three deltoidal cusps, this one over here, this triangle is homothetic to this osculating center defined triangle, meaning its corresponding sides are always parallel between these two triangles. And mysteriously, the ratio of areas of the outer or the cusp triangle by the osculating center triangle is always equal to 4, irrespective of the position of M and the aspect ratio of the original ellipse. So you can see here that it is 4. I'm going to change that aspect ratio to some other number, for example here. The ratio of areas continues to be 4. So if I animate this system here, I get all the same phenomena. The three circles meet at M. You get the concurrence of the three diameters at M. And the ratio of areas between cusps, the triangle defined by the three cusps, and the triangle defined by the three centers of the osculating circles at the preimages is 4. So let's change A here. Just keep an eye on this 4 here. I'm going to change A. Let's make the ellipse be very eccentric. For example, here, you continue with the same system, you continue with the same ratio. So M is effectively, since these three lines meet, so the lines, let's reduce the aspect ratio a bit. So what I can say here is that since the lines that connect vertices of the cusp triangle to the vertices of the osculating circle center triangles meet at a point M. M is a perspector between these two homothetic triangles whose area is invariantly 4, invariant on M, and invariant on the aspect ratio. How cool is that, guys? Thank you very much.